Okay, well, we're here with Pravega.io. We're a sandbox project at the CNCF. And we're focused on data streaming as a storage primitive. So what is Pravega? Pravega is a horizontally scaled storage system with a stream as the fundamental storage primitive. So a stream is akin to a file opened in append mode, but writes can be sharded across the routing key space regions called segments. And in Pravega, writes can be ordered or unordered. So writes can specify a routing key to deterministically identify a segment by these routing key ranges, or writes can be assigned to a segment at random. In Pravega, the segments, or what you might call partitions, look like this. Down at the bottom, we have time, and then on the y-axis we have the routing key space. And so, maybe unlike other sharded systems, you can see that Pravega partitions can kind of be can cover different regions, or can be different sizes, but basically we can start with partitions. Those partitions can subdivide into more partitions, and partitions can join back together over time. The splitting and merging of segments occurs according to throughput, as we can see in this kind of heat map. As over time here, as throughput decreases, we have segments merging, and then as throughput increases, we have segments splitting again. So what is Pravega really? Well, it's a tier 1 storage. It's a log and a streaming cache. This is high throughput distributed write-ahead log for durable writes, and then there's a 2-tier for long-term storage. This is pluggable adapters for S3, file system, HDFS, etc. So what Pravega provides you is fast acknowledgements on tier 1 with efficient and transparent migration to long-term storage. This is kind of a more detailed view of the architecture diagram, but we have data sources on one side. They can work with streams directly, or key value tables, or state synchronizer over streams and segments. And on the other end, you have data processors that are tailing the stream or processing stream data historically. So some of the benefits, we get from Pravega over other competitors, everyone has transactions, everyone has event streams. Long-term retention for tier 2, Kafka's catching up there, but drivers are not open source yet. Pravega and Pulsar have long-term retention in the open source world. Pravega and Pulsar are durable by default, but Kafka, you've got to change some configs right now to do that. And then kind of what's kind of exclusive to us, or this auto-scaling story, the ability to ingest large data such as video, due to some double buffering we do with the segment store. We're efficient at high partition counts. We have consistent state replication and key value tables. So that's kind of just the story at a very high level. I'll turn it over to Brian now to show a demo of scaling Pravega end-to-end in Kubernetes with Flink. Let me stop sharing. There we go.
Yeah. Okay, so next I'll talk about the auto-scale end-to-end at cloud, from storage to computing. Let we look back with Pravega again. What is Pravega? It is a streaming storage. It is built on top of stream abstraction, but it also provides the aforementioned like batch and by-stream APIs. And it supports durability and high performance and scalability. And the the most important part of Pravega is it supports automatic tiering, which our competitors like Kafka and Posa do not have. And it also supports transactions. And let me introduce the Flink. So Flink is a streaming processing engine. And it is also like similar to Pravega, it's built on the stream abstraction that focus on real-time applications. It also provides not only stream primitives, but also have abilities for stateful processing, unified batch API, and also SQL and table API. And as a processing engine, it can support many use cases such as real-time ETL, complex event processing, and real-time AI. And for performance, it is the same with Pravega with low latency and high throughput. And it also supports scalability, while we can in production have millions of nodes of deployment. And it also supports fault tolerance. So we can see that Pravega is a storage and Flink is a processing engine, and they are both built on top of stream abstraction, which can give us this view. So we can have a unified model to abstract the storage layer into Pravega and the processing layer into Flink. And in the middle, we would provide the Flink connector for Pravega as a unified runtime, which we can support large, historic, and low latency real-time data. So next, I'll share more details about the main topic, which is end-to-end autoscaling with these two projects. So here is the motivation. Load variations can originate from seasonal spikes, such as day and night, weekdays, and weekend. For example, the traffic in the city, it may goes up in the rush hours. And also we can see like holidays, non-holidays, and some accidental events, such as like earthquake, vibrations. So therefore, in the real world, there are many use cases that the load can vary at a very high scale. So normally in the current architecture, the load and the resource look like the following in reality. So the resource will have a constant load of resource. For example, you have some dedicated virtual machines or physical machines. So that is limited, but the load is you can fluctuate. So we can see there are two things. First, when the load is below the resources, these resources are wasted. And when load is over the resources you can handle, then you will have the service a service downtime or lower quality. So in ideal, we would like to achieve the following case, that the resource we use can change with the load, so that we can maximize our usage with the resources. And when the load is low, we can save those resources, which save the electricity usage, be more sustainable, and also we can use these resources for other use. So let's more abstract our challenge. So we would have our storage here, and in our architecture, based on the streaming case is more and more popular, these data source can coming from like videos and sensors from IoT. So it will be a streaming storage, which Pravega can fit very well. And on the right-hand side, we will have some data processors to deal with the data, process the data, and generate the values of the data. So left-hand side, we will have the load like this. But on the right-hand side, we will have the processors. So how can we see the scaling with that given the load and this processor, so that we can save resources, and we should also provide the same quality of service with the limited resource. So here is our solution. We would provide a whole solution based on Kubernetes with our storage abstraction with Pravega and our processing engine as Flink. And in the middle, we would have our metric server to listen to the Pravega metrics. And then we will have some autoscaler to listen to the metrics from the server, such as the segment counts, and reflect back to Flink to tell Flink when it's time to scale. So the benefits we choose these two systems is that they both support elastic scaling. From Pravega side, we would have two levels, the logical and physical. In the logical, it is defined on stream level. In stream creation, you can define a service level agreement based on the scaling policy, either by byte rate or event rate for each segment. And on physical side, we can also support that with our Pravega operator based on Kubernetes. You can deploy with a Helm chart easily, and the segment store replicas can scale in Kubernetes by load. So let me next talk about Flink. So Flink autoscaling, it is feature complete on Flink 1.13 based on Kubernetes deployment. It can automatically adjust the parallelism by some custom metrics and leverage the Kubernetes Horizontal Pod Autoscaler to scale Flink task managers. And with the new reactive mode introduced in this release, it allows the application to use all the resources available. So in our case, we can set our custom metrics as Pravega segment counts so that it can reflect the load of the ingestion so that it can scale from end to end. So next is our demo. So we can see this is the Dell EMC Streaming Data Platform UI, and it is showing the monitoring scope of Pravega with test stream. So it is a predefined stream with a scaling policy with 8 events per second. And we are simulating a writer with a sine wave of load so that we can have a high peak load of 100 kilobytes per second and with lower to 0 bytes per second. And we can see with our auto scaling feature enabled, the segment heat map can show like this. For example, if we have some segments reach 1600 events per second constantly, it can trigger the split of segments. So it can split into 2 segments. When the loads are low, for example, here it is below 400, then it will trigger the merge so that 2 becomes 1. That is the logical autoscale aforementioned. So next, we'll have a look at the Grafana dashboard. So here is the Grafana dashboard for Pravega metrics. So we can see for this stream, we can see the write throughput is like this, a sine wave. And meanwhile, we can see the segment count is higher up to 8 at this time. And then when load goes down at like 14 o'clock, it is going down to 1 here and goes up with that load. So with that auto scale, we can see from this part, the max segment write bytes per second is becoming more smooth. So next we'll go with the Kubernetes. So we're using kubecontrol to see what is our deployment. So we can see what is our deployment. So here we can see we are starting two Flink jobs. The first one is a comparison job with no autoscale turned on. And the second, we are turning on the autoscale, which is this project. And also, we'll have our Prometheus to listen to our to gather all the metrics from Pravega, and next we'll have a Kubernetes Pod Autoscaler described next. Yeah, so let's see if we describe the HPA, we will see a task manager autoscaler is configured. Here we listen to the metric segment number, which is reported from Pravega. So we can see currently we'll have one segment. So here in the pod view, we can see only one Flink task manager pod is spawned. And in the history, we can see in the events, it can scale from 5 to 1, 5, 4, 3, 2, 1 over time. So it is working as configured. So next, we can see the combined dashboard from Grafana. This shows both the metrics from Flink and Pravega. So on the left-hand side is the physical point of view. We can see in the segment counts, it is coming from Pravega with highest 8 to lowest 1. And with the help of the horizontal pod autoscaler from Kubernetes, we can also see the Flink task manager is also scaled with that similar wave. And on the right-hand side, we can see the throughput. So remember, we have configured two jobs. The first is the comparison job, which does not have the autoscale enabled. So this is the green line here. So we can see in the green line, it is the straight 2 kilobytes, while with the yellow line, we'll have the autoscale enabled. We can see the sine wave, which means it can catch up, while in the green line, it is bottlenecked with the limited resources, which can indicate if we do not have our autoscale, we will have some service inability. And we can also see the Pravega unread bytes, which is the backlog data we read. So with autoscale turned on, we can see we'll have constant 0 in the yellow line, which means it can catch up with the latest data. While on the other hand, if we do not have autoscale enabled, we will have constant increasing backlog for Pravega, which means your latency of data will become higher and higher, and there will be more and more data stuck in the whole pipeline. So that also proves the importance of autoscale. So that's all for my part, my sharing for the end-to-end autoscale. Yeah, so next we'll go on with our another demo with a more fancy use case based on video processing. So let's see. Hi, Jingjing. Is there any connection issues? Okay, we can see she reconnects. So let's wait for a few seconds patiently.
Hi, sorry, let me share my screen. Hi, everyone. I'm going to introduce a typical use case of Pravega in manufacturing. Here, Pravega will be the storage.
Sorry, cannot
Can
see
you
your
hear me?
screen.
Let me
You do
reshare.
not share your screen.
I was able to see the screen.
Can you see my screen?
I can see it.
Oh, sorry, I just re-log in because my network is unstable. Okay, I'm going to introduce a typical use case of Pravega in manufacturing. Here, Pravega will be the storage layer working with GStreamer, Flink, and Elasticsearch to bring a real-time cloud-native solution to manage quality data. Well, let's start by the background. Germany officially proposed Industry 4.0 at Hanover Industry Fair in 2013, and IoT have become part of the central stage of digital transformation. It connects everything, whether sensors, cameras, or machines. When it meets edge computing, it's possible to process massive data in real time. In this revolution, industry manufacturers are facing opportunities and challenges brought by the new technologies. They hope to take lead in this change, and the quality control of the manufacturing line is a good start point. So what do they expect for quality control system? Let's check the problem. The traditional manufacturers do quality control generally based on two ways. One is manual inspection by skilled workers. As the wage of the worker is rising year by year, the cost is getting higher and higher, not to mention the low efficiency and the high error rate. So they expected the new system can enhance their overall product quality, increase their throughput, mitigate obsolete and cumbersome manual inspections, and save cost. Another common way is to adopt quality inspection equipment, but this kind of equipment is usually very expensive and also have a certain service life. Therefore, we propose a new solution. We leverage the low-cost IoT devices to collect streaming data from assembling line and do analysis in real time. We build cloud-native apps to be running on Kubernetes, which can ship faster, reduce risk, and dynamically grow. So this is our video detection solution from edge node to data center. Leveraging Pravega as a storage platform, Flink as a streaming processing engine, Elasticsearch as a historical analysis tool. Let's take a look at the overall architecture first. The detail of each part will be introduced later. We take each factory as an edge. Each factory can have multiple devices. The video streams are captured from cameras processed by GStreamer and the AI module. The raw video stream and the detection result will be saved in Pravega. Then Flink reads Pravega stream for further analysis. such as real-time monitoring, alert, and statistics, and then tier the storage historical data to the data center. After connecting the historical data of each edge, the data center can use other analysis tools such as Elasticsearch to create an index for long-term archiving and statistical analysis. The historical data can also be used to optimize the model and improve detection accuracy in the edge side. Okay, we will take PCB detection as an example to explain the technical details of each step in the whole pipeline. The first part is data collection. Here we create 3 streams in Pravega, the yellow ones. The first one is the raw video stream. This one is read directly from camera by GStreamer. We store it in Pravega Stream through Pravega Sync. Then the detection module reads the raw stream, this one, detection module, reads the raw video stream from Pravega and process it through the AI algorithms provided by customer. In this example, we use OpenCV and a well-trained OpenVINO model to do classification on each frame of the video. Then a few defects can be detected. Here is an example of the detect result. The 4 defects are outlined by the red boxes here. The detection module will output 2 streams to Pravega. One is the processed video stream, outlined by defects, which can be read by GStreamer and played by video player. The other one is the metadata stream, which contains the video metadata, the detection results, and the image details. The metadata stream will be the input of the Flink tasks. User can also create more streams for different purposes. Next, let's go to the Flink processing on the edge node. The Flink cluster reads the metadata stream from Pravega connector and then create a few pipelines for different processings. In this example, we create 2 pipelines. The first pipeline is to implement a real-time analysis and alert. We use Prometheus reporter to calculate the sliding window of defects number grouped by devices and factories, and use Grafana to visualize the result. On Grafana, we can send alerts to various services via webhooks, for example, Slack, Twitter, email, etc. In this demo, we use DingTalk. Once the defects per minute exceeds the threshold, a notification will be sent to admin's phone. The second pipeline, this one, is used to tiering the historical data to our data center in batch mode. Finally, in the data center, we deployed Elasticsearch to analyze the historical data. The Flink clusters from each edge node through the Elasticsearch sync tier the data to Elasticsearch clusters in batches. Later, from the data visualization tools, managers can see analysis reports of factories across the countries. They can find the potential problems and arrange the production activities more efficiently. Meanwhile, technicians or data scientists can further analyze the detection result, such as tagging the result or correcting detection errors. At the same time, in the background, we can use the fresh data to further train and optimize the detection model. And this model can be updated in edge node to further improve the accuracy. To summarize, We provide an end-to-end solution for unified batch and streaming processing from edge to core, which includes not only the real-time quality detection on the edge side, but also statistics and training in the data center. And its cloud-native architecture that can be easily deployed, scaled, and migrated to other industries. Next, let's see a demo which was recorded by Lingling Yao.
This is demo from Pravega team. First, let's start up Elasticsearch and check its status. Next, start up Pravega and validate if it's up. Next, start up the video detection for edge side. The left video is the raw video from the production line. The right video shows the detection result. The defective state of the chip is marked with red rectangle. This metadata print in the background is the metadata of the result video. Next, play the result video. Then start up Flink. Open the dashboard of Flink. There are two Flink data pipelines responsible for real-time analysis and alert for every production line. Next, open Grafana dashboard. Configure Jinjin for alert and test. There is one alert is sent by Jinjin. The edge dashboard is shown for the result of real-time analysis and alert for 5 production lines. After a while, alert is detected and sent by Jinjin. The dashboard of core side is shown for the historical analysis for 5 production lines. Besides, we can search or query the details of chip metadata. For example, the picture of the chip detection result can be shown in the website. Start up Flink in core side for model training. It can be applied to the edge side for more better detection result.
Okay, that's all for my demo. Thanks everybody. Let me stop sharing. Stop it. Okay.
So, yeah, so that's what we had to show today. Let's see, do we have any questions? I'm looking in chat. I don't see anything there. I don't know if attendees can turn on their mics and ask us anything. I guess there's like, what, 10 minutes left in our time slot? If anyone watching has questions, I guess they could ask, or we could... Can you compare Pravega with Kafka in terms of processing messages? And do you have some disaster recovery as Kafka Mirror, for example? So I guess comparing Pravega and Kafka in terms of processing messages. I guess at a high level, Kafka, has this Kafka record. You populate a Kafka record with like a key and a value, and you have the headers and that sort of thing. In Pravega, we don't really have a message format. We take your event in bytes and we prefix that with like a length prefix, and that's really all we attach to your message. And then we store that on retrieval. You kind of just get back your message. If you want to, like, in that sense, I guess Pravega doesn't record routing keys. So if you need to preserve routing keys in your message, you'll need to know where your routing key is in your message and how to extract that after you've retrieved your message. In terms of disaster recovery, I guess Pravega attempts to achieve that on its tier 1 distributed log storage. We do have, I guess, geo-replication through, you can do stream-to-stream copying processes very similar to Kafka Mirror or a Mirror Maker. We have a few examples of that. You can kind of roll your own, or we have some tools that where you can start up the stream copying plugin. There's some Flink tools where there's Flink stream copying that you get pretty natively with very little work. So you can kind of do, I guess, geographical distribution of streams in that way. But I guess that's a type of disaster recovery in a sense, but our first level of disaster recovery is through the tier 1 log, which is kind of like a write-ahead log for a journaled file system. If a segment store fails, then we read that log to recover the state of the segment store, and then to continue transferring that data to tier 2 or your long-term storage. I hope that answers your question. I don't know if you have other specific questions. Yeah, definitely check us out and give us a try. It works pretty well on Kubernetes. It's the operators are a part of the project, unlike Kafka. Maybe that's another comparison. With Kafka, you have to get proprietary operators from, I think, Confluent or open source operators from Bonsai or Red Hat. Whereas with Pravega, the Kubernetes operators are part of the Pravega project. So yeah, join our Slack and check it out. Any other questions? I guess there's about 5 minutes left if anyone wants to drop any more questions in the chat. Maybe another comparison to Kafka, partitioning is static in Kafka. If you try to scale a partition in Kafka, you can kind of force that to happen, but the new partition won't be pinned on the timeline where it should be. So when you go back to read the partition, you'll sort of get out of order events. You'll be reading the new partition kind of at the same time as you're reading the old partitions.
Yeah, just add something to Derek's points. So yeah, the partitioning is also different. Just like my demo showed, we have the auto scale feature so that it still support the ordering guarantee when we scale, and it is seamless. In Kafka, if you want to scale, it should be manual, and for the downside, it will be a great effort to transition all the all your downstream applications to do that. But in our case, it'd be better. And then another comparison would be the performance. So you can check with our blogs. We have some detailed comparison on the performance. And especially in a very large scale scaling, like over 100 topics and over 100 parallelism, Pravega can have a better performance compared to Kafka.
Yeah, so we sort of do, we combine writes into segment containers. So there's a type of a double buffering that goes on there, whereas Kafka just relies on the file system cache, which can scatter writes all over the place. Let me show maybe our GitHub organization. So we're at github.com/Pravega. Pravega is the main repo. That's where the Pravega server, the segment store, and the controller software is at. We have several operator repositories. The Zookeeper operator, this is quite popular. It's used by Bonsai. The Bonsai operator for Kafka uses our Zookeeper operator. We've got our Flink connectors repository. That's what Brian works on. Our Pravega samples, there's an extensive list of samples in here worth checking out. Our Pravega operator, that's what deploys Pravega to Kubernetes. Video samples. We've got a GStreamer plugin, which is pretty cool. There's a Spark connectors. The Bookkeeper operator is pretty fundamental to it. We've got a Rust client, so to get native wrappers for other languages. To do the GStreamer connector, we use the Rust client. We've got a schema registry. Presto and other connectors use that to interpret what's on the streams. We've got our GStreamer connector, which uses the Rust client. We've got some Keycloak plugins, benchmark tools. This is gRPC gateway. It's kind of an interesting way to adapt Pravega messages to a gRPC connectors. There's someone published bindings for this in C#.net. Our Presto connector, so this adds Presto and Trino ability to query streams with Presto and Trino. There's connectors for both projects in there. Our sensor collector framework, this we actually use this in production at a few client sites, the Flink tools. This open messaging benchmark, this is, we've done it on our blog. You can see some extensive results where we've measured ourselves against Kafka using the open messaging benchmark. And then some experiments with SNMP traps or a connector to Boomi, experimental Kafka adapter at the API level. We'll continue to invest in our sort of Kafka compatibility story in upcoming releases. We have got a NiFi connector, an ingest gateway. This is for just receiving JSON events over HTTP. And then just a few more examples. So quite a number of repositories. The Pravega itself, the charts and the operators are the main ones. And of course, without Presto connectors, Spark connectors, Flink connectors, and so forth, there wouldn't be much to use. So our big focus, I guess, is expanding the ecosystem of connectors and, driving our feature completion in Pravega. So I guess we're at time. We'll probably see people drop off to the next sessions. Thanks for joining us. We hope you're enjoying KubeCon. Any last questions? Or I guess we'll go ahead and stop the recording and end this session. Yeah, thanks everybody. We really appreciate it. Enjoy KubeCon. Bye, Ryan. Thanks a lot. Bye, Ling Ling, Ching Ching.
Bye.
Bye.
Byron. Thanks.
Bye.
Bye.
Bye.